So this talk is actually about two research tracks that John and myself, ended up animating during the first 4 weeks, actually, after the first workshop. And in this joint venture, I played the role of the engineer and John the role of the mathematician, I would say. But okay, we try to understand each other. So before I come to my slides, I would like to take the advantage here to say thank you for the opportunity that was given to me to spend 4 months here in the Isaac Newton Institute with all these people and excellent conditions. It allowed me to stop smoking, very important. That was not to get applause, but to see the Brexit story from the inside, or let's say from another perspective, and which is not finished. So let's go to the presentation, and I will give the word to John for the last part of the presentation. But so these two research tracks were focusing on what I call the TSO and also to some extent the DSO problem, which is essentially to maintain the lights on, and to maintain the lights on at a reasonable cost, ideally at the minimal cost. And this is, of course, as all of you know, in the context of lots of changes going on in our system. And in particular, I would like to stress the fact that we have an aging grid infrastructure. Most of the lines in our power systems are 40, 50 years old already, and many of them have been built roughly at the same time. I'm talking about lines, could talk about transformers and so on. So they might reach the end of the life roughly at the same moment, not so far away in the future. So this is one important thing which motivated to have one of the research tracks specifically focusing on the maintenance issue as well. And then, of course, you have the shift towards renewable energy sources, and also the fact that we have lots of new ideas, technologies and so on that will come up, and of course of which we should be able to take advantage. And like storage, flexibility products and so on. So from an R&D point of view, the problem that we try to tackle here is to develop better methods for reliability management of power systems by combining in a suitable way data, models, physical models, I think it's very important, or mathematical models, and algorithms, of course. And this is to manage problems over timescales, a very broad range of timescales, as is shown here in this slide. For reliability management, of course, the last resort situation is real-time operation. That's really where the operator has to do everything he can do to avoid service interruptions. But then you have a little bit ahead in time, or a few hours to a few days, maybe several weeks, operational planning. And this is one of the topics on which one of the research tracks has been focusing. But then if you go back further ahead in time, you have asset management, maintenance, scheduling. So when to take lines out of operation to do their maintenance, for instance, but also how much maintenance you have to do over the years in order to maintain the system suitably fit enough. So that's the maintenance budgeting problem, which is actually also one of the problems we try to address during one other research track. And of course, further ahead in time, maybe 10, 20 years ahead in time, you have to think about building possibly new lines to connect the generation to the load centers, right? And retiring some other lines. So we had these two research tracks. Both of them were 2 weeks duration, and lots of people have participated there. And there are some documents that will be publicly available in the future, so I'm not spending time here on the details of who did what and what we did actually, but In the first research track, we looked at the so-called look-ahead operational planning under uncertainty. I will come back in the next slide to explain this a little bit, but here we are talking about the planning horizon of a few hours to a few days. And like buying reserves in order to be able to balance the system in real time, for instance, these kind of problems. And there we have looked at both continuous and discrete time optimal, stochastic optimal control formulations. And well, I think it's important to look at this problem also in continuous time, because I think the speed of the dynamics of the power systems in the future may well change because of changes in inertia, for instance, so that these time steps that we are typically using today may not be suitable anymore. So for the research point of view, I think it's important to look at it also in continuous time. And so there is a report that has been written and that will be made publicly available at the end of the program. But I will talk a little bit about the benchmark proposal that we made for that particular problem. And then for the second research track, which was about budgeting and scheduling of maintenance and replacement of power system components, where we look at horizons of a few months when we talk about scheduling outages for maintenance activities, and several years or several decades actually when we talk about deciding how much money we have to invest into maintenance activities to maintain the system in suitable conditions. And in that research track we have been looking actually at two different problems. And the group participating in that research track more or less split after a few days in two subgroups working on these two aspects separately. And one of them is formulating in a correct way the budgeting problem. So what I mean by that is, how much do I have to invest as a TSO or an owner of a transmission grid over the next 10, 20 years in yearly maintenance activities, and what kind of activities I should have in order to avoid, for instance, a situation where in 15 years from now I would have to replace too many lines and there is not enough time to do that, so that maybe I have to anticipate and do some maintenance activities earlier. But this problem, I mean, this is a very vague statement of the problem, so the question is how to correctly state this problem in order to be able to address it. And this is something we are still working on, so we don't have a good answer to it, but hopefully in the future, after the program and work will continue on that topic. And then another important problem that we addressed here in this particular research track with another group was about modeling failure rates of, or probabilities of failures, if you wish, of lines or more generally power system components. So of course if you do maintenance, more maintenance means more reliable components, so in principle smaller failure rates. And question is whether it's worth to invest into that, where is the best place to do this, and so on. But the first thing we need to solve here is to understand what are the failure rates of different components in the power system, how they are impacted by maintenance activities, how they are impacted by operating conditions, and so on. And this is not a solved problem. So I think that this is an important research topic to encourage future work. And again, in this research track, we also ended up with the benchmark proposal. And I will talk a little bit about this benchmark as well. So why benchmarks in general? Well, if you have in a certain research topic a good benchmark, then researchers will use this benchmark in order to try out their methods, to compare their methods, and it will make the research work, I think, more relevant and easier to reproduce. And so it will avoid duplication of work and contradictory publications which would be just related to the way you do your empirical validations. And this is something which we believe should be improved in the field here. And so that's why certainly one good reason to define better benchmarks for some problems. And of course this will allow people to do work in a more easy way if we provide good benchmarks. And if these benchmarks are well agreed with industry so that they reflect the practical problems that industry has, then if we can show that the method works well thanks to these benchmarks, it should also help us to transfer the results of research in a faster way towards industry. So it's very important to have the industrial experts in the loop when you define these benchmarks if you want this particular thing to happen. So therefore, what we try to do is to define the scope of these two benchmarks, which I will explain in collaboration with industry. And we took advantage of this program to start discussing with some experts from industry to do that. And also we need help from industry to collect real world data and see how we can share them in an open fashion with the research community. And then once the benchmarks are defined, one way to foster research is to create competitions. This has been done in other fields, has worked quite well, and it's a nice way of attracting especially young researchers to try out their good ideas on the problems. And so the idea to couple the benchmark with competitions as well. Okay. And so why did we in particular look at this during these two research tracks? Well, because during the first workshop of this program, actually the problem that lots of work do not really go towards industrial application because industry thinks, okay, the model is not really correct. These people have forgotten important practical details, and also because in the research community itself, people do not recognize sometimes the value of methods because the validation protocol is not sufficiently clear or reproducible. And so we thought, okay, let's try to work on that as well during these research tracks. So I go a little bit faster now. The first one was about look-ahead operational planning under uncertainty. So the kind of problem that we want to look at here is seen from the TSO point of view. How much and when to buy generation reserves. And this is, I mean, you can generalize this idea a little bit, but basically when to decide about some control resources that you have to reserve in advance in time. And in order to be able to balance the system in real time, and of course, while taking into account the network constraints, more generally the security stability constraints of the system, and of course what you want to avoid is to be obliged in the last resort to do some load shedding or wind curtailment. And of course you can imagine many different ways to try to build such strategies. So we are talking about a horizon of a few hours here. And what we want to do with this benchmark is to foster research in methods which would be able to automatically build these strategies from data and models. And so we want to provide a test system, data, and a simulator to support this research. And we had very useful input from experts from National Grid and RTE, the French transmission system operator. And so that even though, as you will see, this benchmark is super simple, it is relevant and seen as relevant in their eyes. So the system that the most simple system that we could think of, which would reflect the fundamental nature of this problem, is composed of 3 areas, which in the most simple model would be represented by 3 single nodes, and where you have wind generation, classical here called thermal generation available, and some demand, and then you have interconnections between these areas which may limit somehow the flows between these areas. Okay, and so we decided together about the most simple V1 model here for this 3-area system, where we will have a linear set of equations to reflect the relationship between the flows in these lines and the injections at the nodes. So we neglect essentially here the reactive power and voltage types of problems. That is for later versions of this. And as I said, we also neglect the detailed topology of this system for the time being, but again, this can be refined in later stages. So this is simple enough to allow maybe understanding what we are doing while still being relevant, because there is at least one mesh here for this transmission system. Then we had to think about how to represent uncertainty. So we are talking about operation planning, look ahead about over a period of about 24 hours. And so we discussed with experts, in particular from other research tracks, and also with the industry, to find out what would be a good standard way of representing uncertainties. So the conclusion of that is that we would represent uncertainties as a set or an ensemble of trajectories. And in this simple model, these trajectories would be at each time step characterized by 6 numbers, which are the wind generation and the load, the demand, in each one of the 3 areas. Because we want to, of course, to model the correlation, the dependencies between these quantities in a suitable way. Okay? And then the idea is to publish to the research community a very large ensemble of so-called training scenarios that could be used by people to do research and to define policies, and to keep aside a set of test scenarios, ensembles, that could be used to compare different look-ahead policies in a suitable way, in a non-biased way, without overfitting. Okay? And then the work plan, so this is what has to be done now after the program, is to define these data. This work has already started to some extent. So the physical model of our system, how we can simulate the behavior of this system over 24 hours when it is controlled in a certain way, the technical constraints, cost functions, and then we have 3 control layers. So the look ahead, the real time, operator decision if you wish, and the automatic control of the system. So you have frequency control and things like that, which are in the end going to operate. And then we will design a simulator, and this will be provided as a software, open software, to the research community so that they can play with that simulator. And the simulator will be used to simulate a given control policy over a given trajectory, and to repeat this for a large set of test scenarios and compute performance indicators. And these performance indicators will then be used to compare different strategies, how good they are in terms of reliability and cost and things like that. Okay? And then, of course, we have to define the testing and validation protocols and plan for future versions of this benchmark. And the second benchmark, I will go a little bit faster, is about estimation of failure rates. So we started with a data set from BPA, so this is Northwest US transmission system operator, and where we had recordings of line failure events over the last, I think, 15 years, and some additional information. And so we started to think about how can we use this kind of data in order to determine failure rates of lines, and how these failure rates would be influenced, for instance, by the length of the line, also whether the weather conditions are normal or extreme, and things like that. And then we realized that actually the number of failure events in such a data set, so 15 years for a very big transmission system, is not so high. So we have about one failure on average per component year. Okay, so this is really not a lot to estimate all these failure rates. So there is a lot of research to be done to improve better methods, to develop better methods which can somehow pool the data among different transmission components, even data from different transmission system operators, and possibly even pool data from distribution and transmission to better understand these and better model them. But we cannot really publish this raw data. Most of the TSOs would not agree to publish the raw data directly. So the idea here is then to use the real data to build synthetic models and use the synthetic models to generate fake raw data. And of course we have to document how we do that so that it is agreed by the research community as being realistic enough. Okay? So now I give the word to John for the last part of the presentation.
Thank you very much, Louis. I realise that I'm in the delicate position of standing between us and lunch, so I'll just say a quick word of thanks. Thank you really to everyone who's been involved over the past 4 months. It's been a privilege to have been involved in organising this event, and it's great to see many of the research track leaders here today in particular and able to have some exchange with each other, perhaps for the first time. Okay, so I'm going to just say a few words about a project that unexpectedly emerged during the past few months. It itself is not a research project. I would describe it as an enabling activity. And it has the working title Wrangle. And it's a platform to post and solve data-centric challenges for infrastructure systems. So I'll just give a quick who, what, why, and when. This is a very intentionally open source and openly collaborative effort, which is open to all. Initial discussions have involved, as Louis hinted, participants from the first couple of research tracks, and also some colleagues of mine from the Alan Turing Institute in London. So when we are thinking about infrastructure systems in this context, we're thinking about their complexity. So whether that's due to their sheer size, whether it's due to the fact that there are human decision makers in the loop, whether it's due to high dimensional exogenous uncertainty, which is an input to the system, that complexity will be in common in the challenges that we are thinking about. The challenges, as Louis very nicely described, will be data driven, And we want the data sets that we provide to, as closely as possible, represent the data sets that are in the hands of the problem owners out in the real world. So data sets might be historical, they might be synthetic. Part of the data that we'll be providing, again, as has been mentioned, will be typically a simulation model of the infrastructure system and its inputs. Clearly, we'll be starting with energy system challenges. So Louise described 2 power system challenges. There's also a multi-energy system project that's going on at the Turing, which we intend to feed in as a challenge on the platform. But the idea is to be open later, once we know a bit more about what we're doing, to other infrastructure systems. So one could think of transportation, water, other utilities. And of course, if we get there, then we're able to then potentially explore interactions between those systems, which is a topic of increasing interest. The whys are just those that Louis presented before, but I just want to emphasize that this project's really something that simply emerged. So during the first workshop, we had a discussion on how to bring excellent academic work closer to industrial use, and the message came back very clearly from the industrial colleagues in the room that benchmarks could be a good way to do this. And Giannis mentioned just this week in his opening talk that when people start to work together from different disciplines, it can take 2 years plus for them to start speaking the same language. And certainly we experienced that during our own research tracks. It took us a surprising amount of time to formulate the problems, and indeed on one part of the second track we're still not there. And so again, that's why we think that there's value in us carefully formulating these benchmark challenges for the community. We are underway in a soft sense. If you would like to hear more as the project develops, either as a user or if you'd like to understand how you might contribute to the project, then please just tap your email address into wrangle.org. We've set up the time for our first conference call. That's going to be on the 12th of June at 4 o'clock Cambridge time. And you are welcome to join us. So happy to take any questions about the project, also to Louis.
Thank you. Ready for some questions?
I have a comment regarding the toy or the reduced stylized power system. It seems that it's purely thermal. There is no hydro.
In this first version, we decided no. We would
You are
like
really
to
out quite a
have
lot
hydro, pump storage, and things like that. It's a little bit oversimplified, maybe, but we thought maybe we would start with the most simple version.
I have a clarification question on failures. Do you just have failures of the wires or also of generators? And on generators gets very tricky because they can bid or not bid, right? So it can be gaming or they physically fail. How do you deal with that question as you assess the reliability?
Yeah, so in this, let's say, work we consider for the time being, again, version 1 of this benchmark, no failures.
No failures of generators?
Everything is, in terms of security, is somehow plugged in the limits of the transmission.
Okay.
Chris?
Which would be, let's say, simplex with just number of
Yeah, general question on something arising from Louis' part of the talk. So in the IEEE Power and Energy Society, I'm involved in overseeing the reliability test systems. One issue we've come to here with some of these matters is that I mean we want we want test systems to be for general purpose, but on the other hand, to provide things that people can use, it's easy to get down the track of rather than providing a particular real-world problem, to provide a test system that's already based on, say, a particular type of time series model. And we never really came to a resolution of that as to in these sort of more complex types of problem, how far down the track of setting things up you should go in a test system. And I'm just wondering whether that was something you had some thoughts on arising from the discussions at the Newton programme.
But I think it was a real super good opportunity to bring together several expertise and willingness to work so as to build up this kind of benchmark. We really need, on the one hand, we need to be able to simulate the physical behavior of that system in a realistic way. On the other hand, we need to have reasonable uncertainty models. We have to have reasonable models of what are the available control actions and so on. And we think nothing like this is really existing. Of course, you have these IEEE test systems with some data and so on, but still the way they are used is really difficult to reproduce. So we wanted here to have something which is, let's say, redesigned from scratch as simple as possible, and which can be provided as a service to the community with the simulator.
Yeah, and I think until we always had the difficulty in the Power and Energy Society. Well, there are two things there. One, it's a volunteer organisation, and given the greater complexity of systems these days, it's proving difficult to update these things purely on a volunteer basis. So it's really an effort at NREL, which is providing the people time now. And that's been very helpful. The other is that when it comes to things like models of renewable resource as opposed to simply providing raw data, we've not yet been able to come to a consensus on what it is useful to provide.
Hopefully, this will be a starting point for something that would be improved over the years and remain open software, open data.
Yeah. I'm interested in what you're modelling about the maintenance and the business value of the maintenance and the economics. And are you just modelling it as it's done today, which is, I guess, largely manual? And the reason, I'll explain the reason I'm interested in. I work with the Industrial Challenge Fund on robotics in extreme environments. And one of the areas that we're looking at is inspection and maintenance for offshore structures, and wind farms being one of them, but we're trying to make the business case for the investment in more often maintenance, because if you've got the robotics you can do it more often. So it seems like that would be a great opportunity to look at what the cost of maintenance, the value of maintenance today versus what we could do with robotic systems.
So the maintenance research track is actually a result of a European project called Carrefour, which looked at developing probabilistic reliability management over the whole spectrum, from pre-development to real-time operation, including maintenance. And in this research track, we focused essentially on the definition of the budgeting problem, meaning how much to invest over the next 20 years into maintenance of the transmission system, roughly to say. So when to do that? And we have to take into account the fact that when we do some maintenance in the power system, we take typically out of operation a line. Okay, this will reduce the reliability of the system in operation during a couple of weeks, if that maintenance activity takes a couple of weeks. And the system is designed roughly to be N-1 secure, meaning that you can take one, in some area, you can take one line at the same moment out of operation while still being roughly able to operate the system. Now, if you have to do maintenance of several lines at the same moment, then you would have big reliability problems, and so therefore you have to spread the maintenance over several years. Some lines will have to be maintained earlier than strictly needed from their fitness point of view, just because the time window available for doing that, I mean, you cannot wait until the last moment. And so this problem of modeling let's say, how much we should anticipate, how much maintenance activities to do in more general is what we call the budgeting problem. And as I said, we did not yet converge on a good mathematical formulation of that problem. But certainly you have to take into account the fact that if you don't do enough maintenance early enough, then you will end up in a situation where the reliability of the system will go down, or in other words, where the operating costs of the system will go up very high. And this is something that you have to avoid. So you have to have in your model not only the way maintenance impacts the fitness of an individual component, but also how this component helps the whole system to serve the whole demand, and what is the impact of having a higher failure rates of a particular component on the reliability of the system, and what is the impact of taking the component out of operation for maintenance of the overall system. And I think that makes the nature of this maintenance budgeting problem a little bit different from the one that exists also for the maintenance of wind power plants. But I think there is less coupling in some sense between different.
I would like to suggest that to go for lunch, unless there's something really pressing. Not, let's thank the speakers again.